Okay, so here we are on Monday, and we're going to go over something new. We're going to try something new today, and instead of using a Zoom, which I don't think I could have made it today, so this will take its place. I'm going to go through the same things that we do in normally a Zoom meeting, but so I've recorded the following for today's lesson. And today's lesson being alternators or generation of AC circuits, of AC signals. Okay. Now we've basically covered DC, and you all did very well on the exam, like I said. You did very well. So we're now ready to do AC. AC makes it a lot more complicated because there's a lot more to contend with. Mainly that AC circuits use uh, inductive and capacitive reactances, which means that there is power that's being dissipated due to these reactances. It's not useful power, but you do need it because so that to run the entire program. Okay, so we'll cover that a little bit. Um, let's just take a quick look and see what is involved in today's lesson. Okay, I'll give a quick review of the DC and AC inductance. Okay, what's the difference between, of course, the DC, just creates a permanent magnet, but the AC is a lot different because not only you're making not a permanent magnet, but something that keeps changing on you. And because of that change, you've got a reactance. And because of that reactance, then you get a changes in, you have to look at the power being dissipated, how much power is actually being used up by an alternator that's not non-useful, okay? Um, that's the reactive power. That is mostly lost in your armature voltage losses. So we've got a review on that. Okay, it's a very important thing that you go over that. We also recognize that in an AC circuit containing an inductor, inductances, that energy is stored. Okay, and we're going to be actually using some DC permanent magnets in in the in a lot of these machines. Okay, but when we load up an induction, okay, it basically uh, increases a power. Okay, you increase the power that's generated and is retained in your coil. Okay, so you have to be careful on slowly releasing that energy that's stored up in that coil. So we'll do what is needed is a flyback diode, and you'll have a little spiel on that. Okay. And then finally, we get to today's PowerPoint presentation, which I will go over right now. Okay. So today's main subject is alternating current generators. It's chapter 12 in the new book. Uh, in the It's a yellow book by the same author called Alternating Current Fundamentals. Okay. So we're going to in the presentation, we're going over to general types of alternators, okay? And what the operation is of a specific type, the more widely used one is the rotating field generator. Go over factors and effects that you can have, okay? Because whenever there's magnetic interferences or whatever, you're going to have some kind of effects. Then we'll go over the operating factors and measures. Okay. So let's continue. Let's start up with the AC alternator. And basically what an AC alternator does is we're converting mechanical energy to electrical energy in the form of AC current. There are two types of alternators that are used. The one is called a revolving armature, which has low usage, okay, and it's very simple. Something that you've actually learned about last week, but it's slightly different. And the other is the revolving field, which is brand new to you, okay? But both types generate AC current, okay? In this case, though, the stator, which by definition is a stationary armature, okay, stationary part, and you've got a rotor, which is a revolving part also given by definition. So the revolving armature, okay, is like a DC generator, but it uses slip rings instead of the commutator, so that there's no voltage or current reversal. Because what we're doing is actually changing AC into the poles themselves. The AC is picked up in the poles. Okay, so it basically exhibits low power capacity. And what you need, though, is to excite the fields using a DC method. All right. And again, since it's AC, we need to consider reactive parameters because it's AC. Okay. And here's a picture of the revolving armature. Okay. As seen, you've got slip rings and the armature itself that rotates in around these field coils. And the other one that's most important is the armature is in the stator instead of the rotator. Okay. The coils are set in the slots in the frame, and the armature is used using thin laminates, of course, to reduce eddy current and heating. So the rotor itself sets up fields using slip rings, and they're DC powered for magnetizing the coils. And again, we use laminated poles of two different types. Okay, the higher the voltage, higher voltages can be generated from the revolving field, but the output is from the stator, not from the rotator. So low vibration levels, what you get is low vibration levels, and so you get a greater stability on your output, okay, because of it. So looking at the revolving field, simply put, is a rotator. Rotor is a laminated north-south pole. It's a magnet, okay? And as that rotator rotates, the stator coils experience variations in the magnetic field as they whiz by them, whiz by the coils. So the output is from those stator coils as an alternating voltage fashion, which is sinusoidal. Sinusoidal because this guy is rotating. Okay, the rotor is rotating. So there are no slip rings for the simple device. Okay, because we want to maintain the north-south as a constant on that rotator. So here's a diagram showing a simple alternator with a rotating magnetic core. And we're only using a stationary wire for a stator, okay? And so the current is induced in the stator by that rotating magnetic field in the rotator, by the rotor. Okay. So this is called the salient pole rotor, okay? This is the first device. A salient pole type of rotor consists of a large number of projected poles, as you can see here, okay? And it's mounted on a magnetic wheel, okay? The projected poles are made up of laminations to reduce eddy currents. And the rotor winding is provides these poles. It is supported by pole shoes, okay? Those pole shoes. Right. So salient pole rotors get large diameters, but short on the axial length. So the axial is actually kind of short, and it's generally used for the lower frequencies, 100 RPMs to 1500 RPMs, versus the cylindrical rotor. Cylindrical in shape, having parallel slots in it to place the rotor windings in it. It's made of a solid steel, and also sometimes we call them drum rotors. They're smaller in diameter but have longer axial length. So before we had short axial, and here we've got longer axial but a smaller diameter. Okay, and here we had larger diameter but smaller axial. Okay, windage losses are, as well as noise, is less compared to the salient pole because there's less rough going, and the construction is robust compared to the salient pole rotors. And we can have usually either two or four poles, and we use damper windings are not needed. Okay, so there is flux distortion, and that's it's sinusoidally. So sorry, the flux is distributed actually to give you better EMF waveform. Sorry. The cylindrical pole rotors are used mainly in nuclear, gas, and thermal power plants. Okay, so I suspect probably you have similar types used in your atomic subs. Here's what the cylindrical rotor looks like. It looks just like a rotor with a lot of coils inside it that are being supplied some DC current to magnetize it, okay, to magnetize that rotor. And that rotor, as you can see, is smaller in length, but still have a considerable good diameter. So the DC inputs is to coils. Okay, we've got DC inputs. Remember, you're creating a permanent magnet, and you have by using coils. So you're loading up the coils, and you're not, and since it's not AC, they don't get dissipated. Okay, they are essentially charging up and stay charged up until you have to turn the machine off. You turn the machine off, then current wants to keep continuing to to keep going. And so what we need then is a way to switch it so that you can leak out that current that's charged up into that field. Okay, you've got a discharge resistor here that so slowly leaks out the current. Okay, leaks out that current to ground, all right, so that you don't create a large spark. And you can regulate that somewhat also using a field rheostat as well. Okay. We may, in order, you can have a self-excitation by using a brushless exciter, okay? In other words, if you connect something to this axial here, this thing is turning around, okay? And you can create some more, you can, because this is rotating, all right? You can change from that mechanical rotation, you can change to get some DC current out of that using a armature winding on that axle that creates pulse DC. It creates pulse DC, which is rectified to give you those pulses. Okay, and then them joined together very closely, then we just get a small ripple current on that, and that current, that ripple current, then can be fed to the coils in the rotor. So that's the brushless exciter. Okay. And on the pole winding configurations, okay, we can have either a situation where you've got a series arrangement, okay, or we can have a parallel arrangements, okay. For maximum voltage, then we will use a series, because then we can basically serially, the current is added up serially. Whereas in a parallel situation, we have numerous voltages that you can sum up. As you can see here, they're summed up. Each part adds up to get the current, all right? Total current. Now, AC-wise, one of the most important things is we can have three-phase. Three-phase energy is the most efficient way to produce energy. Okay, don't forget, when we're creating a generator, we got to send out energy to houses and working places and a lot of factories. Okay, those factories, in many instances, use three-phase, not single-phase AC. Three-phase AC then will can be created by an alternator, all right, that sends out high voltages. Okay, in this case we're going to get very high, kilovolts, even maybe higher kilovolts that has to be sent out so that we have enough power to energize all the homes that we need to, in the factories and in the business areas that we need to supply energy to. So we use three-phase that can allow us to do that. Of course, we have to use special materials because we are talking about extremely high voltages, and we need to insulate that to some extent, okay? Otherwise, at the high kilovolts, we can have a situation where we can actually create sparking, okay? Sparking, or just sparking right through an insulation itself by breaking down the insulation. So we have to use special materials. Here in this case, what we're doing is we're getting three different voltages outputs, each tied to a ground. Okay, and because they are each tied to a ground, we can expect this to be a Y configuration instead of a delta configuration, where the delta configuration are all these E points are all tied together at one point to get a common neutral. Okay. So let's take a look at the operation of a rotating field that produces an induced voltage. So we've got here current going in and the A point and the B point, it comes out of the, so we've got current going in A, coming out of B, okay, due to both the north and the south polarity that's inducing this type of current. So electron flow in conductor A is going in, flows in conductor B is out, and pole pieces alternate between north and south and are dovetailed into the rotor. Okay, you can see that that's a dovetail shown right there, okay, so that it doesn't come loose. Okay, it's a good, safe way to keep it tight. And what we get out of A and B is this sinusoidal curve. We get our AC signal. So the induced voltage and frequency, the voltage dependency depends mainly on the flux density, B in Gauss, measuring Gauss. And it does that through an active length of the armature conductor, which is the length is in centimeters. And we have to consider also the velocity of the armature conductors, which is measured in centimeters per second. Okay, so the equations to figure out how much voltage is induced, we use the vector cross product, because the voltage itself that's going to come out is going to be a vector. Okay, the voltage has a polarity to it, so it has a direction, so it's a vector, and we use a cross vector, B cross L cross V divided by 10 to the 8th, and we know where the 10 to the 8th is, right? Because 10 to the 8th is 100 million. Okay, 100 million feet lines are being cut. Okay, to give you 1 volt, and so depending on how many lines you have times the speed, the voltage, okay, will give you something like ampere turns, pretty much. Right. So the frequencies, though, frequency dependence is dependent on the poles and the speed. Speed, we said the speed in RPMs and the poles are just a straight number. So then the force, the frequency sort of is the number of poles times the speed in RPMs. So for example, it would be 2 times 60, or 2 times, we have to divide by 120 in seconds to get back into seconds instead of revolutions per minute. Okay, we have to reduce that to seconds. So we've got that equations there. Our frequency is normally in hertz, cycles per second. So here's a method we could use to get field current control, okay, using that rheostat right there. Okay, there's our DC excitation source. From here, they're going through a rheostat, which is a resistance value that regulates the amount of current we go through the input field, okay? And for three-phase, then we get three different phase outputs, right? And each one we'll call T1, T2, and T3. We get a three-phase alternator output. So we need constant speed for fixed frequency and terminal voltage. And the rheostat, which is in line with the excitation source, allows us to adjust the field so that we get that fixed frequency. Okay. So the three-phase output is regulated by the excitation field using that rheostat. And the terminal voltage will depend on the load current, and therefore there's dependency on the load circuit. Okay, the load circuit, since it's three-phase, you're going to have induction and so forth. It has a power factor, and so we have to look at the armature winding or the armature winding impedance in the armature. And here's a bunch of curves depending on whether you're unity power or leading power or lagging power. Okay, how you achieve full load current. Okay. And so now we have to consider how much power is required to get what you want out of your alternator. And for that, we have to look at the armature voltage losses. Okay, we got an AC circuit, which has an RL circuit in it. And the RL circuit then has resistance as well as inductive reactance. So the current lags the voltage, okay? There's our load hooked up to the output, okay? And we've got a certain amount of inductive reactance here, and we've got a resistance, an I squared R power, okay? We got I squared R power, and we got I squared XL power. That's in there as well. So basically, then we have V induced will be the voltage itself is a vector quantity of the inductive voltage, inductive reactance, and the resistive portion of it, IR drop, plus the total voltage produced. Okay, so we have a produced voltage, we have an IR drop, and we have a reactance voltage. And here's an example you can go over slowly on your own to see how we get from current to the voltage drops and the amount of induced voltage that we get out of such a device. So now then we have to consider the power. Okay, how do we consider power? Well, we might have introduced a load as both in possibly lagging or leading power factor. So you've got additional power that needs to be considered using this particular array. Okay, so using that, then we create diagrams that vector diagrams or that you're familiar with to figure out what's the contribution that we have to add for the lagging power or for the leading power. Okay, lagging power up top, leading power below. Okay, leading power factor. Okay, gives you how two different ways that you can get the power to be different. We're still going to get some armature reaction. The armature reaction, though, is going to be a more complicated situation because we're no longer using DC. DC, we've got some AC building up here. Okay, we're building up AC in the stator, okay? And so we have to, the reaction is very different. And it depends then if it's leading or lagging power, okay? So we can see here, we have several cases. It's a case where we can, where we have lagging power, and a case where we have leading power gives us two different types of armature reaction. So we come up then, in order to discuss that, we first come up with what we call a synchronous impedance. A synchronous impedance is a ratio of the open circuit EMF that's produced, okay, with no, essentially, there's no load. Okay, there's no load, but we can produce an open circuit EMF. And basically it's a VEMF, okay? And we can also create, we can short out the output to get a short circuit current, okay? And then we get the ratio of these two to give a synchronous reactance. In other words, this time it's synchronous because it's not really powering anything. Okay, you're not powering a piece of machinery. Okay, so it's synchronous, and both values refer to the same field excitation. So the synchronous reactance XC is just the ratio of VMF to IC, ISC. We can measure that simply in a single phase by just using a voltmeter and an ammeter. Okay, we can short it out to get the short current. Okay, shorted current, and we'll get a open circuited EMF from the voltmeter. So synchronous impedance is going to be open voltage circuit divided by the voltage of the short circuit, okay? And the reaction is given by the square root of Z squared plus R squared, simply, okay? Synchronous, and here's a way of, you can go through this to see how the synchronous impedance can be measured using all these parameters, okay? We can create an automatic voltage control for three-phase by using, we've got the exciter generator, okay? It's going to be creating some kind of excitation that we can control using a rheostat here. We will look at a relay coil that then is fed into the output to adjust for any variations in your excitation. Okay. So the terminal voltage changes from changes in load changes. So we get current and power factor affecting the armature reactance. Okay, that can change. So relay A senses the phasing between the two phases. Okay, relay A. Okay, and where am I? Sorry, went too far. And B contacts close and open several times per second there because of what's going on with the loading. Okay, and the exciter generator is affected by the added input of the relay and the RC circuit. Adjust the field to obtain so nearly constant DC excitation voltage, which you want to assure that you've got a well-balanced three-phase output. What comes into play also is the magnetic saturation. Right? So this is basically, you're looking at the hysteresis curve. This is a very thin hysteresis curve, and you're really going to look more closely at the knee in which the biggest changes occur. Okay, so that's part of the hysteresis curve for a magnetic alloy. Okay, different alloys have different hysteresis, and the curve depends on how the magnetic domains can line up or unalign during the field changes. Okay, so that's how you get you've got a hysteresis here, and between the differences of the two, you can get added effects. So the circuit for measuring saturation current then becomes a way of using two rheostats, an ammeter, a voltage output measurement, and what is F? And possibly a frequency detector to make sure that the frequencies are in tune. Okay, here you're getting a frequency between change between T1 and T2. All right, remember you need that to be balanced as well. That's going to be 120 degrees for three phase. Okay, and finally we get to alternator data, and each alternator you've got a little tag that tells you what the voltage output is, the frequency that it runs at, 60 hertz, voltage output, volt amperes, okay, and kilovolt amps, okay. That's because it's going to deliver kilovolts, okay, and certain amount of amperage, okay, and so forth. So you can read all these different, tells you what kind of, what are the characteristics for the alternator, okay, that you have. Now, in some cases, you may need to boost that. You need more than one generator, okay? So you can have multiple generators to assure that you've got enough voltage and current being fed. So you do that in parallel for backups and also for capacity. So the output voltages, though, must be equal if you're using more than one generator. And the frequencies must also be equal. Otherwise, you get all bumpy, it bumps, okay. The output must be in phase due to synchronization methods, okay. And that is it. Okay. So what we have then there is the alternator, mainly the drum type or rotor type. Okay. We can take a quick look. There we go. No, that's the wrong thing. That's the wrong thing. No, sorry, can't do that. Okay. Well, you can take a look at it and see the different things that are available to you that to help you out and better understand AC. Okay. Tomorrow we will get into some pretty exciting uh, new types of motors. Okay. Motors that operate on AC. All right. And the types of discussion tomorrow is the inductive motor, which is the most widely used motor that there is. Okay. So it's kind of interesting on how that works. Works on three-phase current. Okay. And the timing then is dependent on the timing between the three different phases. Yeah. So that's how that particular thing works. So we'll discuss about that, go over that tomorrow. So that is it for today, but I can be reached by cell phone, okay? I can be reached by cell phone because I won't be at my house, all right? I'll be at my son's house and I can be reached by cell phone should you need me. So good luck and I'll see you tomorrow.